Hi, and welcome to this video. I'm Manuel, CSC for Aruba, and in this video, I will cover two updates for the child border capability coming with AOS-CX 10.13. So the first one is the ability to get VLAN extension between fabrics attached to the same child border. And the second update is the support of layer 3 multicast routing between fabrics attached to the same child border as well. Okay, so here is the standard agenda that I will cover during this video. So first, we'll have an overview of those new capabilities. Then we'll move forward with the use cases. The details, we'll have the configuration aspects. We'll then have the best practices, a troubleshooting part. It will also include two different demos for the two capabilities that I will cover. And we will finish with the scalability and performance. Okay, so let's start with the overview. So first, just a bit of terminology. So when we talk about fabrics, different names can be used to specify a core device, an access device, etc. So at Aruba, we are using the following terms. So when we talk about data center, we will use the term leaves and spine. On the other side, when we talk about campus, we will use the terms cores and access. So why do we have those differences? So mainly because in a campus, cores will often be connected to each other, and so will form a VSX cluster, which will allow to create a logical VSX VTEP to connect endpoints, routers, firewalls, and so forth, and so to use a core as a border as well. This won't be the case in a data center context, as we want the spines to be independent and pure layer 3 devices. So the connection to external networks and resources will be handled by fabric borders. Okay, so the first update is about the support of layer 2 extensions across fabrics attached to a same child border. So let me just take my pointer. Okay, so first, just a reminder, the child border topology supported since AOS-CX 10.13 allows multiple EVPN-based fabric to share a single border VTEP, which could be standalone or VSX cluster. But before AOS-CX 10.13, this topology supported only layer 3 VNI to be used across multiple fabrics. So it means that only the layer 3 traffic was forwarded between fabrics attached to the port. The layer 2 traffic was only restricted within each fabric. So we cannot get layer 2 extension between those two fabrics that you can see on the diagram. If you need more in details on this topology, so on the child border topology by itself and how to configure it, you can obviously refer to the related TOI, which was hosted in 10.10 on that topic, and that you can find on our Wikipedia or on YouTube. So as we mentioned, since AOS-CX 10.10, layer 2 VNI were restricted to a same fabric. So the bump traffic was not able to be forwarded between eBGP fabrics because forwarding between eBGP tunnels was not supported. So the capability to forward traffic between different tunnels in a multi-fabric context was only supported when the inter-VXLAN bridging mode was enabled. But this mode is only restricted to iBGP to eBGP tunnels. So this is an issue for child border topology because all tunnels are eBGP based. So to solve that, we can now configure each fabric with a dedicated broadcast domain, allowing the bump traffic to be forwarded across different eBGP fabrics and legacy traffic to be forwarded as well between different eBGP tunnels. To do that, the concept of broadcast group ID has been introduced in AOS-CX 10.13 with a dedicated roadmap attribute, which has been added as well, and which is called local broadcast groups. So this new attribute allows to map VXLAN tunnels to different broadcast domains, and that's what we will see in the next coming slides. Okay, so the second update is about the support of layer 3 multicast routing between fabrics attached to a shared border. So before AOS-CX 10.13, multicast was not supported at all with the child border topology, neither layer 2 nor layer 3. So with AOS-CX 10.13, we now support the layer 3 multicast traffic between fabrics attached to the same border. So to support that, two features have been added in AOS-CX. And depending on the role of the device, we have first to define the shared border as a multicast border. And also, each fabric will have a multicast fabric identifier. So the combination of both will allow to support the forwarding of the layer 3 multicast traffic between the fabrics. Okay, so now let's see the use cases. So as usual, we will start with the layer 2 extension capability. And so obviously, the primary use case is to be able to extend a layer 2 subnet across different fabrics attached to the same shared border. So Fabric 1 and Fabric 2 share the same border VTEP that you can see on the top of the diagram as part of the same site. In this use case, layer 2 VLAN must be extended over both fabrics, and distributed gateway handles the routing capabilities across the fabrics. So the second point to note is also that EVPN-VXLAN tunnels must not be provisioned between VTEPs of both fabrics. They need to be provisioned only between VTEPs within the same fabric, but also between the VTEPs of a fabric and the shared border. But we don't have any direct tunnels between VTEPs of different fabrics. So the other use cases that we now support as well are the following ones. So the first one is using centralized gateway architecture with a gateway located at the shared border level. Which means that both fabrics on the diagram that you can see here do not have any routing capabilities at the edge. All routing capabilities being done centrally at the shared border level. In the same way, we obviously support pure layer 2 fabrics with a layer 3 gateway hosted on an external device. So it means that even the shared border VTEP doesn't have any routing function, everything being done externally on an external gateway. The following use case is to support layer 2 extension across different fabrics attached to different shared borders. So as you can see on that slide, we have two sites, so site 1 and site 2, with a shared border topology per site. And the layer 2 subnets can now be extended between all 4 fabrics with this new capability, as all tunnels, including the MultiFabirc one, so the tunnels between the different fabrics, those tunnels, all the tunnels are now eBGP based. So with this new capability, we can forward the traffic between all those eBGP tunnels. The use case that you can see now is the support of layer 2 extensions across different fabrics as well, attached to a shared border on one side and with fully meshed remote fabrics. So as you can see here, we have site 1 with a shared border, but site 2 and site 3 have dedicated borders. So we can now extend to layer 2 networks between all the fabrics if they are fully meshed. This is a condition which is today mandatory as of AOS-CX 10.13, and we will see the reason why in the next coming slide. So if we go back on this use case, we don't need to get shared border everywhere. We can extend the layer 2 VLANs, the layer 2 subnets between different fabrics if they have one shared border on one side and dedicated border on the other side. Now let's see the unsupported topologies. So the first one is when the shared border is used as a stub VTEP. So meaning that the shared border should forward layer 2 traffic between static VXLAN on one side and dynamic tunnels on the other side. So as of today, a shared border cannot forward traffic between static VXLAN and dynamic tunnels. The second use case is when the shared border is configured as a centralized gateway and remote fabrics are pure layer 2. So even if it may work on a pure technical perspective, it is not supported because it is not considered as an optimized architecture. Hence, this is not tested and supported today. So this topology cannot be deployed if we have a centralized gateway and pure layer 2 fabrics on the other side as remote fabrics. Now, let's see the layer 3 multicast use case. So the use case for multicast traffic is pretty obvious. So the main goal of this new capability is to support the layer 3 multicast traffic across multiple fabrics attached to the same chart border, but also to remote fabrics. The resource and the receivers are located in 2 different fabrics, but also in 2 different VLANs. Okay, so we'll use also the distributed gateway at the edge level in order to handle the routing capabilities. And it is important, we'll see that in the next coming slide. Now let's move on with some details. So first, an important concept which is introduced with AOS-CX 10.13 is the concept of broadcast data plate. So this concept is very important as it will be used by the 2 new capabilities that we are introducing today. So this new behavior is the ability to automatically attach each VXLAN tunnel to a broadcast data plane as a child border VTAP level. So what does it mean exactly? So once a VTAP receives an IMET route and creates the related VXLAN tunnel, CX will automatically attach it to a data plane, which is set to 1 by default. So just as a reminder, an IMET route is used by a VTAP to advertise the VNI it has configured, and so in which it is interested, which is necessary for the bump traffic management. So this is also known as EVPN route type 3. So by default, coming back on the broadcast data plane, so by default and following the split horizon rule, a border won't be able to forward traffic between 2 VTAPs attached to the same broadcast data plane. This will avoid any issue with loops and so forth. So it means that a border will only be able to forward traffic between tunnels belonging to different broadcast data planes. And by default, all eBGP-based tunnels coming from different fabrics will be attached to the data plane 1. If we now look at this diagram, we can see the following things. So first, tunnels coming from edge VTAP number 1 and edge VTAP number 2 are attached to the same broadcast domain, so broadcast data plane. So due to the split horizon rule, the layer 2 traffic forwarding is blocked between those 2 VTAPs. But in the meantime, the edge VTAP number 3 is attached to a different data plane. So the layer 2 traffic from this VTAP is well forwarded to the other VTAP, so 1 and 2, and the traffic coming from edge VTAP number 1 and edge VTAP number 2 is also forwarded to the edge VTAP number 3. That's because the child border is able to forward the traffic between 2 different broadcast data planes. Okay, so how can we relax this split horizon rule? So to do that, the method already implemented since AOS-CX 10.9 is to enable the dynamic VXLAN tunnel bridging mode. So using this, IBGP-based tunnels will be automatically placed in the broadcast data plane number 1, while eBGP-based tunnels will be placed in the broadcast data plane number 4. This is automatically done by CX. You don't have anything to configure. In this case, a border will be able to forward the legacy traffic and the bump traffic between the fabrics. But with the child border capability, we need to allow also the traffic between several eBGP-based tunnels. So in this case, we'll be able to configure the broadcast data plane for each fabric, allowing the legacy and the bump traffic to be forwarded. So by default, as I already mentioned, all tunnels will be placed in the broadcast data plane number 1. But we can manually configure it using a broadcast group ID, which is newly introduced in AOS-CX 10.13. So doing that, the new data plane ID will be the sum of the broadcast group ID we are configuring plus an offset, which is different depending on the platform. So if we take an example, let's take the 8325. If we want to configure the broadcast group ID at 2, the new data plane ID will be 5 because we have an offset of 3. On the 8360, same thing. The only difference is the fact that the offset is 127. So if we configure a new broadcast group ID at 2, the data plane ID will be 129. A final note for this slide with 3 important points. So first, to sum up, broadcast data planes allow to bridge traffic between every type of dynamic tunnels, which can be either IBGP or eBGP based. The second point is the fact that this new capability is only supported on shared border as of AOS-CX 10.13. So doing that on dedicated border is not supported today. And finally, it is important to note as well that these capabilities to manually configure broadcast data planes is specific to dynamic tunnels only. Static VXLAN tunnels are not concerned, so not supported by this new capability. Okay, so as I mentioned, so the use of broadcast groups in the context of shared border needs to follow some rules. So we will take some examples just to illustrate the rules and how we can interpret, how we can manage different broadcast data planes. So on this first example, we can see that all fabrics belong to different broadcast data planes. So the layer 2 subnet will be able to be extended across all fabrics. This is a standard use case. On this example, we can see that all fabrics belong to different broadcast data planes as well. But in this case, a specific broadcast group has been configured for the fabric number 2, number 3, and number 4, but not for the fabric number 1. Layer 2 subnet will be able to be extended across all fabrics because the fabric 1 will be automatically attached to the broadcast data plane number 1. So each fabric will have a different data plane. So on this third example, so fabric 1 and fabric 2 belong to the same broadcast data plane. So in this case, layer 2 subnet won't be able to be extended across those 2 fabrics because they are attached to the same data plane. But those fabrics can get layer 2 extension to the fabrics number 3 and number 4. On this last example, so fabric 1 and fabric 4 do not have a broadcast data plane configured, as you can see with the blue rectangle. So in this case, layer 2 subnet won't be able to be extended across those 2 fabrics because they are attached to the same data plane, so the default one, so which is the data plane number 1. But those 2 fabrics can extend the layer 2 networks with fabric number 2 and fabric number 3 because those fabrics, so 2 and 3, are attached to different broadcast data planes. And now, how can we extend this capability to remote fabrics? So when the remote fabrics are fully meshed, as you can see on that diagram, we can use a single broadcast data plane as all remote fabrics will have direct tunnels to the others. So it means that the traffic, layer 2 traffic coming from this fabric, if it needs to be forwarded to this fabric, will never go through the shared border. It will always use the direct tunnel between those 2 fabrics. But in the case remote fabrics are not fully meshed, each remote fabric will have to belong to its own broadcast data plane. Otherwise, the bump traffic will not be able to be forwarded between those fabrics because the shared border will never forward traffic between 2 tunnels belonging to the same data plane. Okay, so now regarding the platform support. So as you can see, broadcast groups configuration is only supported today on 2 platforms. So 8360 and 8325. So it means that the layer 2 VLAN extension as well as the layer 3 multicast routing is only supported with those 2 platforms as shared border VTEP. Just a quick note on the Aruba 10,000. So it doesn't officially support the broadcast groups as of AOS-CX 10.13, and so it can only be used for POCs. But in the meantime, this platform can be used today as a border VTEP, but with some key things to take care of. The filtering can be used for hosts, which are directly connected to it when it is used as a border. But a newly introduced command that you can see here, so the uplink -to uplink, needs to be configured to avoid any redirection of the VXLAN to VXLAN traffic to the AMD Pensando chipset. Okay, so now more details about the VLAN extension between EVPN-VXLAN fabric with a child border. So as you already understood, the main issue we are trying to solve here is, and we are solving here, it's not we are trying, we are solving here, is the ability to forward traffic between tunnels belonging to different fabrics and which are eBGP based. So the solution is to be able to attach each fabric to a broadcast data plane as a child border level, and so to relax the split horizon rule between data planes. This is what we are calling flexible selective split horizon. This will allow to forward bump traffic across fabrics attached to different data planes by using a new type of route map, which will be applied to inbound routes from a specific fabric. To deep dive into the broadcast groups and related roadmaps, so the new roadmap introduced with AOS-CX 10.13, those latest will have to be implemented as a child border level only. It's in a very simple way. So doing that, and because the child border only pairs with the route effectors of each fabrics, and once the route map is applied, all IMET routes will allow to automatically map the newly provisioned VXLAN tunnel to a data plane. So if we look at the diagram on the left, it means that all traffic coming from a VXLAN tunnel in fabric 1 will not be forwarded to another VXLAN tunnel on the same data plane, so on the same fabric. But on the other side, traffic coming from a VXLAN tunnel in fabric 1 will be forwarded to another VXLAN tunnel in a different data plane, so in another fabric, because you can see here that we have broadcast data plane, two different broadcast data planes. The fabric 1 is attached to this broadcast data plane, and the fabric 2 is attached to this broadcast data plane. Just for educative purpose as well, it has been decided to use a route map and not a simple peering attribute because it offers much more flexibility as we are able to apply filters on route maps. So looking at the example shown on the top right of the slide, we can observe different things. So first, on each leaf, the VXLAN termination to reach out a remote MAC located in another fabric is always a child border. We don't get any direct VXLAN tunnel between VTEPs in different fabrics. But we can also see, checking the EVPN routes, that the AS number belonging to the child border is always the first one in the path. So obviously, we have the opposite thing on the child border side, especially looking at the EVPN routes. You can see that the first and the only AS in the AS path is the AS of the attached fabric. So some other important details to mention. So while on the overlay, so no, it's not while on the overlay. So as of AOS-CX 10.13, so we support both IPv4 and IPv6 in the VXLAN overlay. Also, in terms of services, VPN services, we support VLAN-based and VLAN-aware bundles. Second point to note, so eBGP must be used between child border and all attached fabric, while iBGP would be used within each fabric. And as we mentioned earlier, eBGP within the same fabric, although configurable, is not supported in AOS-CX 10.13. It's also important to note that a child border cannot obviously be used as a route reflector. And finally, there is no other change in comparison to the child border capability that we know before AOS-CX 10.13. And especially, there is no impact at all on the layer 3 capabilities supported since AOS-CX 10.10. Okay, so in addition to broadcast groups, there is another key point brought by AOS-CX 10.13, which is IMET relay. So in order for a child border to automatically terminate the tunnels between fabrics, the BGP VPN behavior has been modified in AOS-CX 10.13. So it means that now IMET type 3 routes, so the IMET routes, are automatically and natively dropped by the border. But this could cause some issues when the border is not used as a VTEP, but just as a root server. as it must relay the IMET routes between the VTEPs. So that's why a new command has been introduced in AOS-CX 10.13, allow IMET relay. So this command, which has to be used in the VPN configuration context, allows the device to forward, as you can see on that diagram, to forward the IMET type 3 routes received by a VTEP to another VTEP. And so the different VTEP will be able to create and to form a VXLAN tunnels between them. Okay, so now let's move on with some details on the layer 3 multicast routing capabilities. So regarding multicast, the ability to forward layer 3 multicast traffic across two different fabrics attached to a shared border answers to the same requirement than with unicast traffic. We cannot forward back the multicast traffic between two VXLAN tunnels belonging to the same fabric. Otherwise, other VTEPs within the same fabric will receive the traffic twice, from the source VTEP and from the shared border. So to do that, we simply need to configure the shared border as a multicast border. So once done, the border will automatically map each PIM neighbor to a fabric ID, avoiding it to forward back the traffic. So this identification is made using a multicast fabric identifier, which is by default the AS number. So it's highly important to note and understand as well that the solution is relying as well on the broadcast group capability introduced with this release. So to deep dive into this new capability, so first, the multicast fabric identifier is sent by each VTEP, edge VTEP within the PIM-LO packet. So it's used by this identifier is used by the shared border to map the sending PIM neighbor to a fabric. On the other side, it's also important to note that all the VTEPs receiving this identifier won't do anything with it. Secondly, as we already mentioned earlier, the layer 3 multicast traffic forwarding relies on the concept of broadcast groups. So those groups have to be configured on the shared border level, at the shared border level, in order for the multicast traffic to be forwarded between the fabrics. Next, also mentioned as well, a simple command has to be put on the shared border to declare it as a multicast border router. So doing that, it will automatically take care of the MFID, so the multicast fabric ID brought in the PIM-LO packet. And finally, the sources and the receivers can be directly attached to the shared border. The rendezvous point and the BSR can be external to the fabric as well. And the orphan ports on the shared border are supported. So if we now come back on the concept of multicast fabric identifier. So as I mentioned, this identifier is sent by each multicast router in a fabric using the PIM-LO packet. So AOS-CX uses the option 65001, which is in the range of options for private use to send this identifier. So as you can see on this example, on the left-hand side of the slide, we have the PIM-LO packet from leaf1, and we can retrieve the multicast fabric ID in hexadecimal format. So in our case, we have 96, which means 115 decimal format, in which is the MFID that we have configured on the leaf1. On the right-hand side, we see the same type of packet, but with the MFID set to 60 in hexadecimal, to 110 in decimal. So using those values, the shared border will be able to map each multicast traffic to a fabric. Okay, so moving forward with the multicast fabric identifier, so an important point is also how the remote fabrics or the remote borders will be handled. So by design, a remote border, as you can see on this diagram, so this device, which is not part of a fabric directly attached to the shared border. So this remote border, which can be a shared or dedicated, will be able to determine by itself if it is a border or not. And so it will never send the MFID in its PIM-LO packet. So how can we handle that? So the solution for that use case is simply to attach the MFID 0 to all neighbors which do not send the MFID. So that's why it's very important to get all remote fabrics fully meshed, as a shared border won't be able to forward multicast traffic between neighbors having the same MFID. On the other side, if we do a show IP PIM neighbor on the shared border, there won't be any line showing the MFID for those remote devices. So as you can see, sorry, I missed this one. So as you can see, in the remote border entry, we have no line for the multicast fabric identifier. While, as you can see in the OVSDB, it is set to 0 as expected and as designed. So just take care of that. Okay, so let's see some additional details now. So first, this new capability supports both IPv4 and IPv6 in the overlay, but only IPv4 is supported in the underlay. Then the distributed gateway is required, as the routing capabilities must be enabled on the edge VTEP. So the reason why we need to get routing at the edge is because the MFID, so the MultiFabirc ID, will be advertised using PIM-LO packets. It's also important to note that for a given VLAN, the SVI and the active gateway IP addresses can be the same. Also, as a reminder, only layer 3 multicast routing is supported, which means that layer 2 multicast across attached fabric is not supported. And finally, it's also important to note that only PIM-SM is supported. Okay, so now let's see how to configure everything. So let's start with the layer 2 extension. Okay. So as we have seen earlier, the configuration on the shared border requires 3 steps. So first, we need to configure our route map with the new attribute local broadcast group and the ID we want to use. Once it's done, we just need to apply it on this route map on a BGP peer or a peer group within the EVPN address family and in the inbound direction. So 2 things are really important to note. First, we cannot configure those route maps if the inter-VXLAN bridging mode is enabled. It is mandatory to disable it before. It is those two features are mutually exclusive. And the second point is the fact that the configuration by itself, once applied, won't get any effect. You will need to clear the BGP sessions in order for the device to relearn the IMET routes and so to map the VXLAN tunnels to their broadcast groups. Okay, so let's see now a simple example and the related configuration. So on that slide, we can see one access VTEP on each side in different fabrics and a shared border as well as route reflectors. Okay, so the pure BGP configuration on the edge VTEPs as well as on the route reflectors of each fabric remain totally unchanged and as defined in shared border TOI, which came with AOS-CX 10.13. The key thing here is the configuration that we have added on the shared border. So as you can see here, we have added 2 route maps and they have been created into the configuration, one setting a local broadcast group to 1, and the other one setting a local broadcast group to 2. So once done, they have been applied to the BGP peering to each route reflector in each fabric. On that slide, we have now an example of the configuration of a shared border with remote fabrics and dedicated borders. So as you can see, the difference with the previous slide is the add of a third route map with a new broadcast group applied on peerings with the remote borders. So it means that all the remote borders for those 2 fabrics will be mapped to the same, and the VXLAN tunnels coming from those remote fabrics will be attached to the same broadcast data plane. Now you can see an example and the effect of clearing the BGP session. So on the left-hand side, we've got a status of the broadcast group IDs and broadcast data planes after we've applied the route maps. So as you can see, each VXLAN tunnel is still mapped to the default data plane, which is the data plane number 1. But once we apply the clear BGP command, tunnels are automatically mapped to the configured data planes as we relearn the IMET routes. So you can easily observe here the offset between the broadcast data plane and the broadcast group that we set in the route map. So as an example, here we are on 8325. We have set in the route map a broadcast group ID to 1. So once we apply that, doing clear BGP, when we are clearing the BGP stations, the broadcast data plane becomes 4. So we have an offset of 3. So it means that we are on an 8325. Now we can see examples of the different show commands that can be used to visualize the configuration. So on the left-hand side, for the broadcast groups, 2 commands can be used. So the show BGP L2VPN EVPN neighbors or the show BGP all neighbors to see if a route map has been applied to this peer. But also the show interface VXLAN VTEPs details to get information on the data plane which are used. On the right-hand side now, regarding the IMET relay, there is no dedicated or specific command allowing to see the status of this new capability, as in if it's enabled or not. So it is required to check into the running configuration itself in the VPN context. On the API side now, so you can retrieve the different information already discussed through 3 different resources. So to retrieve the content of a route map, and so to check if there is an entry which set the broadcast group ID, you can use a resource on the left-hand side, or the resource at the middle, so at the middle of the slide. And finally, using the BGP neighbors resource, you can see on which BGP peer the route map has been attached. It's also important to note that there is no way today to check which is the broadcast data plane currently in use for a given BGP peer. So you can see if we apply the route map and the broadcast group ID, which could be used by a BGP peer, but the effective broadcast data plane, we cannot retrieve this information using the REST API. You can see on that slide an example of a workflow used to fully configure a route map with an entry setting a broadcast group ID and to attach this route map to a BGP peer. So the only thing to note here is that there is no API to make a clear BGP. It will be necessary for you, if you want to automate this workflow, to do that manually afterwards through the CLI, or if you are using Python as an example, to add a step in your workflow using an SSH model like Netmico, Scraply, I think ASIC SSH, Paramico, and so forth. This is also obviously supported with Ansible. So even if there is no dedicated module for that, you can use the config module to send your set of commands based on config templates, as an example. So to send those commands to your device. And on the IMET relay side, you can retrieve and update this value, so this feature, using the system EVPN resource. Okay, so let's take a look now at the layer 3 multicast configuration. So to configure the layer 3 multicast traffic forwarding, 2 steps have to be done. So first, configure the shared border as a multicast border with this command line. And the second point is obviously do not forget, for it to work, that you need to configure the broadcast group as well. The second point is, it's an optional step, is to configure a multicast fabric ID on each VTEP using the command lines that you can see here. So on the edge VTEPs, you can use IP multicast, multifabric identifier, and you set your identifier. So as we have seen in previous slides, the manual configuration of the multicast fabric identifier is not mandatory. And it's even preferred to let the device take its own AS number, avoiding any misconfiguration. But in certain cases, you may need to configure it. So one example, as you can see on that slide, is when you have the same AS number used by different fabrics. In that case, if you still use the AS number as a multicast fabric identifier, The multicast traffic won't be forwarded between fabrics because all VTEPs will have the same identifier. So in this case, it will be mandatory to configure a different MFID, so multicast fabric ID, per fabric to be able to identify VTEPs and their fabrics on a multicast perspective. So moving forward, let's take a quick look at a simple example. So as you can see with this example, the configuration which must be done is really small and easy. So the only thing to do is to enable the multicast border capability on the shared border side. So this simple command that you can see here will enable layer 3 multicast traffic forwarding in the shared border topology. All the other multicast configuration remains unchanged in comparison to what you already know. Also, as we already discussed, optionally, or if it's required, you can configure the MFID at the edge VTEP level using the command line that we already introduced. So the current slide is a reminder of what PIM configuration should look like. So as you can observe on the edge side, we just need to enable the PIM globally, as well as on the interfaces on which we want to distribute or receive M routes. And on the border side, we also need to enable PIM globally. And because this is a best practice, this is something that we will see in the next coming slides, it's also important to configure this device as a root rendezvous point candidate, as well as a BSR candidate. So once everything is configured, doing a show IP PIM neighbor, we now observe on the edge VTEPs that the interface to reach out the PIM neighbors is the L3VNF. The same way, on the shared border, the interfaces to reach out to the VTEPs, so to the edge VTEPs, is also the L3VNF. And as you can see as well, we also have the information regarding the MFIDs announced by the edge VTEP, which are the AS number by default. Doing a show IPM route and using the group address, we can clearly see here that the multicast routing protocol used is PIM-SM. And depending on the VTEP, the downstream interface will be a local VLAN or the L3VNF. On an automation perspective, the multicast MultiFabirc can be easily retrieved using the system URI. So on the shared border, the related configuration can be collected using the key multifabric_border. And on the edge side, the related configuration can be collected using the key multicast_multifabric_identifier. So using this API, we can then very easily set an automation workflow to set your configuration on the entire architecture. So as you can see on this example, so using such workflow, do not forget to configure the broadcast groups as we have seen in the previous slides. This is also obviously supported with Ansible. So even if there is no dedicated module for that, you can use a command module to send your commands to your device, as you can see on that example. Okay, so the best practices now. So first, the unicast part. So there are three main best practices here. So the first one is to use manually configured broadcast groups for each fabric. Do not necessarily rely on the default data plane for any of the fabrics. It will ease the troubleshooting in case of any issue. The second best practice is about the clearing of the BGP session. Obviously, schedule a maintenance window when you need to modify or to implement the broadcast groups. Then it's also a best practice, when possible, to clear the BGP session only with specific peers or only on specific address family. Otherwise, if you do a clear BGP star, all BGP peering for all address families will be impacted. The third best practice is about the IMET relay capability. So if this capability is enabled, the extended VLAN must not be configured and put into EVPN on the shared border. If this is done, the shared border will also send image routes for its locally configured VLAN, and the remote VTEPs will receive two different image routes for the same VLAN. So this could lead to abnormal behavior and traffic disruption. So regarding the layer 3 multicast, so the best practices are the following ones. So first, it's a best practice to configure the shared border as a RP candidate and BSR candidate. And secondly, it's recommended to keep the multicast fabric ID as default, meaning to use the AS number. So this could avoid any misconfiguration between the VTEPs. And finally, as broadcast groups are mandatory as well, the related best practices that we have seen earlier need also to be followed. So troubleshooting, so let's start with the VLAN extension. So the first thing to do is obviously to make sure that the VXLAN EVPN fabric is up and running. So check the BGP configuration as well as the EVPN and VXLAN interface configuration. Check also on the root effectors of each fabric that the peering with the shared border has the option next stop unchanged configure. So once this is done, check that the broadcast groups are enabled and what are the configuration. Be sure that the BGP session has been cleared, and in case the shared border is also a VTEP, check that the feature allow image relay is disabled. Regarding the multicast now, so regarding multicast, same as for unicast, check the EVPN configuration, EVPN-VXLAN configuration first. And once this is done, check the multicast configuration, obviously. Check also if the correct broadcast group has been assigned to the correct BGP peer in the EVPN address family. Check the multicast fabric identifier learned at the shared border VTEP level, and check the multicast fabric identifier configuration homogeneity on edge VTEP level. Okay, so now the demos. So what I will do, I will show you the two slides for the two demos, for the unicast and for the multicast, and I will then move forward and I will do the two demos in the same session. So for the first demo, so for the unicast demo, we will use two different fabrics attached to the shared border, which is the 8325. So in fabric 1, we will have two different hosts connected on two different VTEPs. On the other side, in fabric 2, we will have one host connected on one edge VTEP. So the goal of this demo will be to extend the VLAN 110 between those two fabrics, and so between those two hosts. In addition to that, the third endpoint will have a layer 3 connectivity to the other ones, as it is located in the VLAN 150. It will be just there to check the connectivity and the potential impact that we could get on the layer 3 connectivity. And so, as I mentioned, we will first extend the VLAN 110 between the two attached fabrics, and we will also extend this VLAN to two remote fabrics that we can see on the top of the diagram, on which we have two different hosts. We have one host on this fabric and another host on this second fabric. For the multicast demo, so we will use the same setup than for the previous one, but with two endpoints connected into two different fabrics. So the fabrics directly attached to the 8325. And those two hosts are located in two different VLANs. So the source is located in the VLAN 110 in the fabric 2, while the receiver is connected in the VLAN 150 in the fabric 1. Okay, so let's move on. Okay, so let me just reconnect my endpoints. Okay. And this one. Okay. So here we have two windows opened. One on this. So this window is this host. Okay, so the 110.30, and the other one is 110.31. So as you can see here, I have three different command windows which are already open with ping already launched. And we can see that I have already an IP connectivity from each host, which is the IP connectivity to the third endpoint to the third host. So it means that my layer 3 connectivity between the VLAN 110 and 150 is already set up. The three other windows are ping within the same VLAN, and so I'm trying to ping the host in the other fabric, but also the host located into the remote fabrics. Okay, so now if I go on the child border. So now we are on the child border. So the first thing that we can do is obviously to check for the EVPN configuration. So if I do a show run EVPN, I can see that my VLAN 110 is already configured. So it means that I can have layer 2 extensions between my different fabrics for this VLAN. So that's it. If now I go back, I'm checking the VXLAN VTEPs detail configuration. You can see as well that all my tunnels to the different edge VTEPs are all attached to the same data plane. So data plane number 1. Okay, that's normal because this is the default behavior in AOS-CX 10.13 when if we don't touch the configuration, if we don't create any roadmap, and if we don't customize the broadcast group ID, all tunnels, all eBGP tunnels are set and are attached to the data plane number 1. So what we can do first is to create the connectivity between those two endpoints. Okay, so the 110.30 and 110.31. So in order to do that, I just need to create, go into config. I just need to create a route map, so rmap1, which will set the local broadcast group to 1. So once it's done, I just need to attach this route map to one of the route reflectors. So in this case, I'm attaching this route map to the routes, the inbound routes, incoming routes from this route reflector. So now it's done. My configuration is done. And now I can check the connectivity. So you can see that it doesn't have any effect. It doesn't have any effect because I didn't do a clear BGP. So let's do that. And we will see in few seconds the connectivity, and that's done. Okay. So if I go on this host, so which is this one, and so this one belongs to the fabric on which we have modified the data plane. So that's why I have the connectivity to all the hosts. So to this host, this one, and this one. If we go on the other host, so this one, I only have the connectivity to the host in the other directly attached fabric. I still don't have the connectivity, the layer 2 connectivity to the remote fabrics. That's normal because I didn't modify the data plane for this fabric. So it means that this fabric and the remote fabrics are still attached to the same data plane. So if I go on my child border and I do a show interface VXLAN VTEPs detail, you can see now that this VTEP is now placed into the data plane number 4. So this VTEP is this one. And all other VTEPs are still in the data plane number 1. Okay? If I modified, so it was not this one, it was the other one, sorry. So .4, which is this one. So it placed, obviously, by default, the other VTEP, so this one, which belongs to the same fabric, to the same data plane. So now, if I modify the configuration, and I had a new route map, number 2, which will set the local broadcast group to 2. And if I apply it, the pairing with this route reflector, so this fabric, it will automatically allow the communication, the layer 2 forwarding between this VTEP, this endpoint, this host, and the remote fabrics. So let's see that. You just need to wait for a few seconds. Okay, here it is. So now you can see that these endpoints now have the layer 2 connectivity to all the endpoints in all fabrics. One key point here is the fact that, as you have seen here, I have a service disruption, which is normal because I've done a clear BGP. So I've restarted all the BGP sessions. And so all the VXLAN tunnels has to be recreated. So that's why I've lost few seconds. And so I had a service disruption. And so that's why also I want you to do that during a maintenance window. Okay, so that's why that was for the unicast part. Now, if we are moving forward with the multicast part, I will use this host as a source. So you can see that I have a video which is running into VLC, and it is currently streamed using the multicast group 239.1.1.1. I will use this endpoint, so this host, as a receiver. So if I launch VLC, open network stream, I'm trying to reach out to the flow, to the multicast streaming, this multicast group. And if I do a play, nothing happens. If I go on the chart border, let's check some stuff. So I show IP PIM neighbors all VRF. So I can see that my two different VTEPs, so this one and this one, are mapped to different fabric identifiers. So this one, which is the source one, is using the multi-fabric identifier 765.0.22. While this one, which is VTEP on which the receiver is connected, it's using the multicast fabric identifier 65.0.12. And the interface for the PIM adjacency is the layer 3 VNI. If I do a show IP mRoute, all VRF, I can see that I have a route learned from the edge VTEP, where the source is located, with an incoming interface, which is the layer 3 VNI. So it means that on a pure multicast perspective, everything works. But as you have seen, I still don't have any traffic on the edge VTEP, so on the receiver. That's only because I didn't enable the multicast border capability on the shared border VTEP. So the only thing that I have to do is to do show multi-fabric border, and that's done. And if we go back on the host, you can see now that the traffic is coming. We can test by modifying the video, and we have the impact. So now we have layer 3 multicast routing between two fabrics using a same shared border VTEP. Okay, so that's it for the demo. So let's go back on the presentation. So the scalability and performance. So you will have the different scalability numbers in that array. Two things which are important. It depends on the device that you are using as a shared border level, or the number of broadcast groups that you can use. But the scalability of the fabrics by themselves, it will also depend on the device that we'll use at the spine or core layer. So depending on the fact that you are using an 8325 or 8360, you won't have the same level of scalability. For the multicast part now, so the shared border VTEP, so you will find in this array different capabilities with the number of IGP entries, number of mRoutes, number of L3 VNI that you can use, the number of VRF and the number of fabrics that can be used with a shared border.